This is only going to work with a series of positive terms. So if you've got terms that are negative in there, you can't do what we're about to do. Um, all right, so we got the same deal to begin with that we were talking about with the integral test. We have terms of a series a sub k that we can write using function notation. And that's going to be okay as long as k is a positive integer. So 1, 2, 3, and so on. We're going to let s be the value or the sum of the infinite series. So if k starts at 1 and goes to infinity of a sub k. And we're going to let s sub n be the nth partial sum, which is the sum of the first n terms of that series. So that would be the sum from 1 to n of a sub k. The first thing that we've got to talk about that's a new idea is the value of r sub n. That's called the remainder. And it's the remainder after the nth partial sum. That's why the n is important. So r sub n is going to be the difference of the actual sum minus the nth partial sum. Okay, another way to think about this statement is that if you took the remainder r sub n and you added the nth partial sum, you would get the sum of the whole series. Okay, that's just same relationship there, just written a different way. All right, so the remainder is also referred to as the tail of the series. Okay, and it's what's left over after the nth partial sum. All right, so the next thing is that this remainder has got to be, r sub n, has got to be less than or equal to the definite integral from n to infinity of our function f of x. Okay, and it's the function f of x that we're talking about up at the top of the screen. And this function f of x is continuous, positive, and decreasing, just like it was before. So our improper integral here gives us an upper bound for the remainder. Okay, now the next statement is that this remainder is kind of trapped between two different improper integrals. If we look at the value of the integral that starts at n plus 1 and goes to infinity of our function f of x, that's going to be less than or equal to the remainder, r sub n, which is less than or equal to the definite integral from n to infinity of f of x dx. Okay, now going back to what's in parentheses there at the very top of the screen. If I add the nth partial sum to the remainder, I have the value of s. So what I'm going to do with this inequality is I'm going to add s sub n everywhere. So what that does for me is I know that the value s sub n plus the definite integral or the improper integral from n plus 1 to infinity has got to be less than or equal to the actual sum of the series. That's an S right there. Okay, remembering that this quantity right there is S. And this actual sum of the series has got to be less than or equal to the nth partial sum plus the improper integral from n to infinity. So what we have here when we're looking at this, the improper integrals, if we have a convergent series, we're going to be able to find the value for the improper integrals. We're going to be able to find the nth partial sum if we know a value for n. So we would be able to find a value for that quantity, and that value is the lower bound for the value of the series. Same deal with the right end of this inequality. We're going to be able to get a numerical value for this, which has got to be greater than or equal to the value of the series. So this is an upper bound for the value of the series. Okay, the lower bound, the notation your textbook uses is L sub n, upper bound U sub n, just so you are aware what that is. So the information here allows us to find an upper bound for the remainder. Okay, the improper integral from n to infinity is going to be greater than or equal to the value of our remainder. We're also going to be able to find a lower bound, a value that our series value has to be greater than, and an upper bound, a value our series value has to be less than. So basically what this last line does for us is it gives us an interval that we know the series value has to stay would be within.